Thank you. Thank you so much. My name is Dario. I'm working for Intel, and today I'm presenting you making AI explainable together with Federated Learning. I'm representing here a lot of people and colleagues working with me. This is a huge activity, and you will see from the results. Of course, it's not something that a single individual can do, but I'm pleased to present you. I believe it's quite remarkable for this event, for the conference. And yeah, just a few things about myself. I'm working for Intel and Standards and Research. I'm also serving as a chairman for an international standard body, which is MAC, Multi-Access Edge Computing. And I took the leadership of our working item in the 5G Automotive Association about MAC for the automotive, of course, working on publications, innovation, patents, and I'm pleased to participate to conferences and workshops, yeah, and many other things. I love also music and piano, so but maybe this is less interesting for this conference. Just a couple of minutes for a video clip, and then we start. Just wanted to.
In the early days of Intel, Robert Noyce once said, "Don't be encumbered by history. Go off and do something wonderful." And wonderful, we did. For more than 50 years, we transformed computing, putting Intel silicon at the heart of innovation. But with all the breakthroughs we made, all the possibilities we created, what's truly wonderful is we did it together. Let's go higher. And today, as we head into the future, fueled by cloud, AI, 5G, and the incredible potential of data, we are united by what we must do. We're making Intel hardware and software a catalyst for a better tomorrow. To protect our planet, make technology accessible to all, and enrich the lives of every person on Earth. Because the truth is, if you have an idea and Intel inside, you have everything you need to go off and do something wonderful.
Okay, good. So we are ready to start now. Okay, yeah. And yeah, this is my agenda today. I just wanted to talk about this approach, for the FEDXAI approach, mixing together Federated Learning and explainable AI, some demonstration about the project. Let's see if we have also the time. I have another video clip to show you the real-time demonstration prototype, some perspective from Intel on the 6G, so about the future. I guess it can be also interesting for you. A closing remark. Okay, so what is Federated Learning and explainable AI approach together? Let's start from the beginning. Actually, we start, of course, obviously, artificial intelligence is everywhere. Also for the future, we can only predict it will be even more pervasive for future systems. But we have also a fundamental need of trustworthiness, which is now important and also requested by the European Commission in a report of ethics guidelines for trustworthy AI. So this is, according to these guidelines, explainability represents one of the key requirements toward trustworthiness in future systems. They are becoming so complex that what happens if they are wrong or everything is correct? If everything is correct, it's okay, but what happens is things are going bad. So explainability is an important value, and in practice we have to understand how we can provide this. Also, not only explainability, but also the need to preserve data privacy for the entire life cycle. So data when you transfer and also when you store in the storage. Okay, so it's essential then to enhance the transparency of a model, define its ability to inherently understandable to a human. That's the key. We should interpret what happened and the reason for a certain outcome of a certain model to understand maybe how to, let's say, intervene, right? Or just to judge what happened. And then let's start on the other side now, federated learning. Maybe most of you knows already. We start from the fact that obviously having multiple sources of information, it's beneficial to have a higher inference accuracy and reduce bias, but also this centralized way to manage data is very impractical. So from a communication, but also computation point of view, and of course, it violates privacy and security requirements imposed by data owners because also we are expanding the attack surface for possible over-the-air attacks. So federated learnings are helping in this privacy-preserving paradigm. And at the end, you have a sort of collaborative AI training models where participants interactively learn and share the model by only transferring local model updates and receiving aggregated shared data model from the aggregator, so without sharing the actual raw data. So you see that, also in the definition from many places, the key point here is have a distributed elaboration of different collaborators for the federated learning paradigm, and this is typically also kind of a natural place to deploy these in the edge computing in Mac. So, of course, we need also privacy. I mentioned privacy and data security. We want to ensure that what we run as a functionality, even in the single collaborator, but also in the aggregator, is safe. And then Intel SGX, software guard extension, is an example. It's a practical way to implement kind of a sort of protected memory where you have your application and data is not exiting unless you don't want to do that. Of course, the code is there in that private region and is secure. And, but of course, it's not enough. And so to have the confidentiality, it's not enough to have SGX. You have also to have the sort of validation and attestation procedure that also provide evidence about the validity of the code, who is allowed to use that, and of course, nobody can change the code at any time unless this is authorized, of course. So, and this is just a way, in a sort of animated picture, how this is working. Practically, you have the different collaborator, the federated learning. They are using a model locally, and of course, encrypted data is just sent to the aggregator, which is putting all together and doing the aggregation model and sending also the model back to the collaborators. And everything inside here is working on SGX. The information sent to the aggregator is encrypted, and as well, the aggregator is running as well its own aggregation model in the SGX area. So we want to mix the two things together. Why? Because, of course, naturally, the federated learning is exploiting this kind of aggregated federated averaging protocol and putting all together the models, but typically this is optimized for some kind of algorithm, typically deep neural network, but is not so far studied enough for in the context of explainability. So really, we want to make FL explainable. We need to bring together federated learning and explainable AI. That's, let's say, the concept that we developed. Actually, we proposed this for an European project for 6G that was called FED-XAI. And we started to work on that, I believe it was 2018 or 2019, and project started also in 2020, and we worked on that activity that finished just June this year, so you can understand how long was the journey. But at the end, this is a concept aiming at adding explainability and inherent interpretability of the model learned in a federated fashion. So I mentioned this European project. I was innovation manager of this project, which was composed by many companies from industry and also research and universities. And it was a European consortium called the flagship 6G project because it was setting the scene for the requirements for what will be 6G. Maybe now you think, oh, maybe we are 2023, it's too early to talk about 6G. Actually, I will say this is not the case. Typically, every system is arriving at every decades and every 10 years, and there is a cycle for which companies are starting to work about the next future, the next evolution, which are the new features that we need to add, put in the standards, and then standards will become products, and the products will go into the market. So there is a cycle. And then for the R&D point of view, we started already 3 years ago with this project, and this was one of the activities, of course, that also was produced together with a demonstration we'll show you. And at the end, we wanted to tailor to a use case. Hopefully it can be interesting about autonomous driving, automated cars. And also I'm going to talk about AI-enabled QS prediction. Yes, we are about to predict the future. Let me explain what is a QS prediction. QS stands for quality of service. So you may understand that if you have a connected car, this is relying on the connectivity and the network, and you need to know, it would be desirable to know what is the quality of this connection, because if you lose it, there is a problem. And then, more than that, we would like to know what happens in the future. If I can predict that the quality will stay the same, or at least above a certain threshold of acceptability. And then, why? Because, of course, this is a wireless medium. And wireless means that nothing can be guaranteed 100%. And especially latency, throughput, these are strict requirements. And especially for critical applications, this can be an issue. If you have QS changes, everybody of us can understand, we have a loss of coverage in a tunnel, in a highway, or let's say in a city behind a certain building. And then, of course, it's something that, okay, if we are just browsing the internet, is not critical. But if there is an application for autonomous driving, and this is going to try to save lives, but fails, it cannot save lives. So, or maybe there is another kind of activity which is for the production in a factory, in a smart factory, you need really to react in real time. This is a critical, mission-critical application. And then you need a reliable, fast, and performant connectivity, right? So QS is key, quality of service. And also, predicting that. So maybe imagine a car, you are moving from a point A to a point B, and you want to understand many KPI, key performance indicators of your network, understand what is the packet delay budget, the parity level, the packet error rate, the bandwidth, and so on and so forth. If you have this kind of information, you can then trace a sort of map of possible service that you can provide in the territory, right? So, for example, in a certain territory, I can activate a certain feature of autonomous driving because the quality is sufficient above my thresholds for that specific service. For another specific service, another color, I have other sort of minimum set of requirements from a connectivity point of view, maybe more relaxed, and then this can be a bigger area, like in blue. Another area in red can be, again, more relaxed in terms of requirements and can give me a sort of better coverage for that specific service. So predicting the QS also is important because maybe a certain service is lasting just a few seconds, but I need extreme high quality in that there's a few seconds, not 1 hour, right? So it's a trade-off about also reliability and performance. And sorry, but the life is not so easy. So a typical scenario in our life is to have multiple mobile operators, multiple car makers. We cannot pretend everybody to drive a Ferrari, right? There are different cars in the streets. And this is the case. So a typical automotive scenario in the real life, it's very heterogeneous. Multiple operators, multiple car vendors, and multiple technology providers for the infrastructure. And this is the case where we have to investigate, and we also we have to work. And we set up a test bed, and we tried a couple of use cases, especially see-through and teleoperated driving. Maybe some of you can know already, but in general, this is not yet something that is coming to the majority of the people. These kind of services are maybe helping the driver to have a better view of the situation. For example, see-through, you can have in your camera in the car, and then connect with the car above a view that can give you the video stream of what the camera is seeing. So you increase your view. If there are obstacles, you have a better view, right? You see through. And the teleoperated driving, of course, there is different flavors operated by a human or an AI agent, but in any case, if there are any issues, you press a button and someone is helping you and taking control of the car. Maybe you go to a safe place if you don't feel well, or if there is any problem, it goes under control of a teleoperator, and it guides your car to a safe place, right? For an ambulance or anything else. And this is a service that can be activated, but needs, again, connectivity, and maybe control, data rate, video streaming, any kind of downlink and uplink traffic that is needed to make the AI working. And you need also AI to predict what is the QoS. So AI is everywhere. Yeah, maybe it's not so important to see. Maybe this is just to motivate that this is one of the key use cases for the 6G. So I'm just giving some flavor. What will a 6G enable, unlock as a possible use cases and services in the future, at least for the automotive. But yeah, this is how we implemented these new use cases. The first one, if you remember, see-through, you have, of course, a kind of video that is played from the camera of the car in front of you and sent to you. And so that you can consume it and have a better view, understand if you can change lane or not, if this is safe or not. And teleoperated driving, essentially, it's a stream, a video stream that is needed for the teleoperator to drive the car for you and send back some commands and then take control of the car. So actually it's a video stream, in this case, only one way. But still we have needs in terms of reliability, and throughputs, and latency, as I said. So here is the demonstration. Just wanted to explain you what's about. Then you have the connected cars, the remote driver, and the need to know in advance what the quality of your experience, the quality of service will be. And because, of course, you want to know if this quality is going to degrade in the future in order to take proper actions and countermeasures. So how we did this? We implemented, of course, the first step is sending a video stream to the Mac, to the edge server, and from the connected cars, and the system is collecting measures, how to do predictions. This is not magic. It's based on numbers and data. You have seen the video before. It's based on the power of data. So elaborating everything based on the data that you can receive, you can understand the metrics, and then collect them, and then do some projections for the future, right? And then each of the UE is a local manager managing the FEDXAI in the FEDXAI architecture, the Federated Learning with a single manager related to a car, and then there is an aggregation sent to done by the aggregator, the FEDXAI aggregator, and the step number 4, this is receiving local models and builds a global model, and finally using those metrics and the global model, each local manager can predict the QoE of the future for the single car associated to it. So we implemented this test bed. It was actually in real time. So you can see here actually is using a realistic 5G network emulation with the Simu 5G environment, and in between, connected with the Ethernet cable with a commercial terminal or a laptop or a smartphone, and sending a video source, and then entering into it. You can see it like a 5G in a box, okay? It's like a 5G network in a box. And then you can collect metrics, instruct the FEDXAI local managers, doing the aggregation in the edge. You have a dashboard because you need the control to understand and how this model is explainable. You make some consideration about the QS and what is the prediction of the QS, what's happening, something is failing, and why. That's the explainability. The dashboard is the place where you can understand, the human can understand what's happening. And then also what is the reason of worse quality, if this is because of loss of coverage or because the radio cell is crowded of users, and then shared mean implies that you have less capacity for everybody, right? So what is the reason? Is loss of coverage or saturation of the capacity? And then you need to understand in the dashboard you have this. And then you have, of course, the uplink video and the video stream with the video player here for the teleoperator. So, yeah, I explained already the modeling. I mentioned the Simu 5G. This was an environment. Actually, it's open source. It was generated, triggered by Intel and University of Pisa in 2019, released open source in April 2021. Since then, they have 6,000 or more downloads. You can download. This is a complete environment where you can do system-level simulations, but also run the simulator in real-time emulator mode. And you can really run a 5G network in a box in a real time with real devices connected to TCP IP to real devices in input and in output, as you can see here in the figure, okay? And yeah, this is what we did, integrated, as I said, the Simu 5G environment with the Federated Learning environment implemented in Intel OpenFL. This is again another open source framework that was generated by Intel and released recently, I don't remember, a few months ago, I believe, in Linux Foundation as open source. So as well, you can find this framework free and open source with many libraries. Actually, the project here contributed to some additional library for the FEDXAI environment. So you can use as well this concept as well. And then, yeah, this was the setup. As I said, you have a real-time environment, you collect metrics, and importantly, we fed this system with the real, because you know this is a simulator, but to be adherent with the reality, we fed with the real data from Telecom Italia live 5G network, right? So actually we used the real data from the network, because in this consortium European project there was also Telecom Italia, we worked with them, and we used the data to feed this setup. And also we used, as I said, OpenFL for the FEDXAI implementation and the dashboard, which is showing the predicted QS. Okay, so what is the expected outcome? From one hand, of course, not only the service itself, which is the video, but step number 3 is we want to understand what is the actual prediction in real time and its root cause. As I said, if things are going bad, why? What is the reason for that? And so that I can understand. And this AI is giving some explainability of what's happening, and then I can intervene or I can take countermeasures. It's really important. Why? It's not important just only for the end customer. The end customer want to have the service, actually, for the service provider, but also for the car maker. They are responsible and liable for that. So the system should provide a reliable service to the citizen, right? But then the car maker itself and the network operator, they should feel comfortable about offering a service which is reliable, and then understand what's happening. Yes, using AI, but also using explainability as a tool to understand how things are working and why they are doing well or not, okay? And this is essential for the business. It's critical because they have to understand, here have the control of the situation in the dashboard to understand what's happening. And yeah, so few details about the implementation, some containers as a de facto standard, so compliance with the edge computing and Mac-enabled environments, using RESTful APIs for handling and integrating application microservices over HTTPS for having encryption for secure communication. As I said, we use the Federated Learning framework, Intel OpenFL, and integration with containers paradigm extended with this activity, with a plugin to support FL and explainability, and repository module, we use the instance of MongoDB in Docker container, and of course Intel servers to run the training. I will show you just a couple of minutes then this demonstration that was also shown to the European Commission. Okay, so this is actually what I presented before. Yeah, thanks for lowering the volume. Not so much to comment, but at the end we have a training phase, of course, and building the model, and then you have to run the entire system and the server, and do the inference model using the live QS metrics in the global model. And you have here the setup of a very small scale prototype, but running in real time. So you have video server, you have here the simulator, the emulator network, Simu 5G, and the video player, actually for the teleoperator driver, and of course the dashboard. As I mentioned, the FEDXAI app. So what's happening? You start in a network emulation, then the video server starts streaming and flowing through the network emulated, and the receiver plays the video. Okay, everything is good. Green lights here, you see, green lights in the dashboard, but maybe now the UE moves while it's served by different radio base stations, and you expect also the QoS to change in 3 seconds. This is the forecast. Maybe from green to yellow, the prediction is to see a worse quality, and then the video gets worse as predicted after 3 seconds because the user is going to the cell border in a worse coverage. So you understand what's happening and why, right? And then of course, you can take some countermeasures because you have a lower quality of the signal, SINR, and but you may have also a prediction that in the future this will become higher again, and then of course the video quality will be better back to the initial case. Okay, so this was a kind of a live experiment showed to show you, but as I said, this is quite business critical because you see it's like two faces of a coin, right? You see a reality from a point of view of what is the user, what is even myself. If I want to see this in my cockpit in the car, I want to press a button and understand if the system can give me reliably a service in a certain area. Is available see-through or teleoperated driving in this area? Yes, it's available because it's compliant with my requirements. And this is what I need. But behind the scene, there is also the need to predict the quality of service, to use AI agents for that, to do the forecast in the future, and make this forecast explainable, to understand what happened, and if I can take some countermeasures, for example, lowering the video data rate to maintain a certain, let's say, fluid video flow, and avoid some freezing of the screen, for example, or other things. In any case, having a flavor about the reliability now and predicted in the future, it's essential for the car makers and for the network operators that are liable for that service to offer to the citizen, right? And yeah, some perspective on the futures. And more generally, so this was just an example, but you know, also in your fields, everybody of us becomes very expert in a very narrow field, and maybe also ignorant in another field. The technology is moving so fast. Everywhere there will be AI, right? I would like to give you a flavor about 6G. Our view is about a AI native and cloud native 6G system. We are talking, of course, about the future, but, well, not so much, because if you see, the trend was always starting from two separate worlds: communication and computation, right? Okay, so, and progressively, those two worlds are also kind of converging. We are seeing that in the future, this will become even more obvious and more evident with a sort of joint computation and communication system. And this is about 6G, what we see for the future for the 6G. So on one hand, you have a communication technologies that are traditionally delivering traffic and data. On the other hand, you have a computation, and then all the AI algorithms. How can they work together? Actually, we have explored that AI, it's also used to improve the technology itself that is used for the communication, so the transmission technologies, the error correction for the packets, the setup of the network automation, many parameters of the network itself. So there is AI for network, but also network for AI. You need also to design a better AI network to support the transfer of the data. You have seen Federated Learning, and then you have different collaborators in the aggregator. But also you have a computation location you need to manage, many locations. So a lot of things are, let's say, on the table to define what will be 6G. I don't have the crystal ball. I don't tell you this is our vision. But I would say this is kind of mostly a consolidated view that progressively is tending to converge across the years. And I'm also in the standardization work, so I can tell you that we are close to that, because the companies are working also to define standards, to define something which will be interoperable, used universally, right? Once this will be done, I can tell you what is 6G. Still, so far I can give you a vision, to be honest, okay? But still, there are quite some ingredients. We expect to see 10 to 100% KPI to improve the digital experience. You need to transfer even more data, services which are data hungry. And a lot of sensors, and in machine intelligence. We need ubiquitous communication and computation, as I said. And then we see also a network that will be programmable and cloud native. And also, last but not the least, we need also security and privacy, of course, but also energy efficiency in the systems, because actually nobody is telling you, but all these AI algorithms are consuming a lot of energy, and a lot of data is to be processed, and this is a cost. So it's in the perspective is not affordable. You should keep the cost of joule per bit low. And this is a challenge. And yeah, these are the, let's say, technology superpowers that we foresee, so from compute, pervasive connectivity, cloud to edge infrastructure, artificial intelligence, and sensors and sensing, okay? And as I said, where we can put our workloads, maybe today we are simply implementing something for the cloud, and we are talking, I've seen some speakers talking this today about edge computing. Yes, this is maybe already pertaining to the domain of 5G. Today, we see 5G and edge computing in some locations. But for the future, we may also see a certain distributed computing environment with different kind of capabilities, of course, bigger servers, but also more constrained devices, and all of those devices can host computing capabilities. And this can be really a distributed system. So this is where the way we are conceiving 6G, also not only AI native, but also cloud native. And essentially, today we are seeing, let's say, data transferred from the terminals going to the network, the radio access network, the core network, and then the cloud or edge cloud if you wish. But tomorrow, for the 6G mobile network communication and computation systems, you may have workloads everywhere, included in the network itself, at every level, from the terminal itself, and the network, and the core, and the cloud. Okay, this is the concept we call Wide Area Cloud, WAC. And this is our top 10 list of technologies for 6G. I will not read everything, but just to mention, maybe just because I'm involved personally in Mac, I'm chairing this standard group on edge computing. Some of these technologies really important and key for the Mac and evolution. I'm trying to push all the companies about that for the future, how we can support 6G. And yeah, my last message, okay, to you. So to finish, moving toward future 6G systems, there is a need for explainable AI and federated learning. I hope you got my point and you appreciated the presentation. And FED-XAI, so is one of the possible solutions. It's a key enabler to support smart and secure 6G services. Last message, maybe not for myself, with great power comes great responsibility. From quoting Uncle Ben. I hope you enjoyed, appreciate it. Thank you so much.